All right, so welcome to week 3 of our weekly Math 2413 reviews. So this week we're going to be covering the precise definition of a limit, or in other terms, we're going to be doing epsilon delta limits, and also continuity of a function. So let's go ahead and begin. All right, so first thing we need to think about is how we've defined the definition of a limit. So in previous weeks, we've just said as x approaches some number, it approaches the of a function, it approaches some limit. But the thing is, that's kind of vague wording. So there's actually something that we can do, because the thing is, we don't know necessarily what approach or close means. Therefore, we have our epsilon delta limits, and what they're going to do is they're going to let us kind of define what close is. So this is going to be like a lot less vague than what our previous definition was. All right, so essentially what we can say is, instead of saying when x is close to some number c, y is close to the limit L, we can say when x is within a certain distance from c, y is going to be a certain distance L. And we can also consider those distances to be what we could call tolerance limits. So let's go ahead and define some things. We are going to let our delta is going to be the distance between x and c. Yeah, we're going to have some constant c. And then our epsilon is going to be the distance between our y or f of x and L, which is going to be our limit. So essentially, we can go ahead and think of this as saying that, so we know delta is going to be our distance between x and c. Well, we could define that as being on either side we can just define our c, like our x as being on either side of c. So essentially and it's the same concept for our epsilon. So let's say so we can essentially write this down as saying that we have our c minus our delta is somewhere in between our x, which is somewhere in between our c plus delta. And like I said, we can think about the same way for our epsilon. So where we have our L minus our epsilon, which is less than our f of x, which is less than our L plus our epsilon. So let's think about what this means in a graph, as a graph. So let's say we have our graph, and let's say we have a function that goes something like this. Let's say we want to find the limit at this point right here. This point is going to be our c. This is going to be at x equals c, and then our f of x is going to be our limit. Well, we can go ahead and think about and define either a delta or an epsilon that can let us decide how close one needs to be in that proximity of the other. So let's say we went ahead and defined our delta as being a certain distance away. So we can go ahead and say that we have our delta line here. It's going to be our C plus delta. Or we can go the other way and say that this is our C minus delta. And if you go ahead and bring this over, these are also going, since these lie on the graph, they're also going to have corresponding f of x values. So we can think of this one right here as being our L minus our epsilon, since that epsilon is our distance between our L and is our distance between L. And then right here is going to be our L plus our epsilon. So now let's go ahead and think about what our precise definition of a limit is. So what we can say, so we have our precise definition of a limit. All right, so we can let some function f and it's defined on some open interval, and it contains the letter A. Or you can go ahead and substitute that for C. Either one is fine. Essentially, it contains just some number within that interval. However, it may not have to exist at A itself. Then we can say that the limit of our function f as x approaches A is some L. So essentially what we're saying right here is that it's essentially saying that we have some limit as x approaches A of f of x equals some value L. But we're now adding a caveat to that. This happens if for every number that we're going to describe as epsilon, or let me repeat that, for every positive epsilon, then there is a number that is some positive delta such that essentially this is saying this defines our distance. So let me go ahead and pull back the pen again so we can see what they're talking about. So we're saying such that if we have if we have our distance set up like we did earlier, this time we're going to rewrite this as we have our x minus A is less than delta. which, as we defined earlier, delta is our distance away from A. Then there exists some f of x minus our limit L that is some distance epsilon, that is with some distance epsilon away. So let's see what exactly we mean by. So let's go ahead and do an example, and this may go ahead and explain exactly what we're explain a little bit more what we're talking about. So let's go ahead and use this to go ahead and this is typically used when we're proving a limit. However, there are a couple other uses that we'll go ahead and show in just a bit. So we're going to go ahead and let's say they're wanting us to prove that the limit as x approaches 1 of our function 5x minus 2 equals 3. All right, so the first thing we're going to do is we're going to set up. So we know that we're going to go ahead and set up our absolute value for both our epsilon and our delta. So we know that we're going at x equals 1, so we're going to have our absolute value of x minus a here, so our x minus 1 is within some distance of delta. So we know that, yeah, delta is going to be some distance away. That's essentially saying that x can only be delta away. And we also know that because this is true, we also know that our function minus our limit is going to be less than our epsilon. So in this case, we have our 5x minus 2 minus our limit 3 is less than our epsilon. So we need to be able to figure out how to relate these to each other. Because if we can get a relation, then we can be able to definitively say, if let's say x is some distance from our A, then we can definitively say, well, then y has to be within y distance of L. So this essentially is helping us be able to actually go ahead and declare, okay, how far away can we move from each value? So let's go ahead and combine this a little bit more. Let's go ahead and change this down to 5x minus 5 is less than our epsilon. Well, there's something interesting going on here. We can go ahead and take a look, and let's just go ahead and factor out a 5 to where we have our 5 times our x minus 1, which is less than our epsilon. If we take a look at this right here, we can see that this brings us right back to this. So what we can actually go ahead and do is to go ahead and move that 5 over to where we can say that the absolute value of x minus 1 is less than epsilon over 5. Well, that looks close to identical to what we have over here when we defined our delta. So what we can do is we can actually use this to define what delta is. So we can essentially say that our delta is equal to epsilon over 5. But we can't necessarily stop there. We have to go ahead and prove that that exists. So we have that our epsilon over 5, so we have that delta, so we're assuming that delta equals epsilon over 5. Let's go and rewrite our question right up here. All right, so now we have to go ahead and prove that delta equals epsilon 5 is in fact true, and that we can use that for any value of epsilon or delta we want to go ahead and apply. So we're actually going to go ahead and think back to what we know earlier. We know that we have our f of x minus L is going to be less than our epsilon. So let's go ahead and go back to that. So we have our 5x minus 2 minus 3. And we know that's going to equal 5x minus 5. Well, as we saw earlier, what we can do is we can plug that in, and we can go ahead and pull out that 5 to get us back to our x minus 1. Well, right here, what we also know that x minus 1 is less than our delta. So we can say that 5 times x minus 1 is less than 5 times delta. And since we said that delta equals epsilon over 5, we can go ahead and say that 5 equals 5 times epsilon over 5. And we can go ahead and pull our epsilon right back out. This actually goes and fits what we wanted to say earlier. Since we started off by saying we have 5x minus 2 minus 3, which is our f of x L, that is going to be less than epsilon. So that's essentially showing how we can go ahead and figure out a relationship between delta and epsilon. So let's go ahead and look and see how we can use an application for this. So let's say we have a function f of x, and let's let it equal x squared plus 1. We also know, and let's say we want to take the limit as x approaches 3 of f of x. Well, we can go ahead and know using our limit laws that that's going to be equal to 10. But we want to be able to figure out how close exactly can we estimate. What's going to be our error given some distance. So essentially we want to say, what is the distance from 3? Like how close to 3? Does some value x have to be? For y to always be within 0.1 of 10. So let's go ahead and look and see how we're actually going to start this. The first thing we can do is we can go ahead and set up how we always normally set up our epsilon delta limits. So we know our distance from x is delta, so we can say that we have our x minus 3 is going to be less than some delta. And we also know that we have our f of x minus L, which is going to be our x squared plus 1 minus our 10, which is our L, is going to be less than some epsilon. But we already defined our epsilon as being 0.1, since epsilon is our distance from is going to be our distance from our limit. So we can just go ahead and plug in our 0.1. So let's go ahead and look and see what we can do with this knowledge that we have now in order to find our delta. So we can go ahead and actually let's go ahead and break up and get rid of this absolute value. So we can say that we have negative 0.1 is less than x squared plus 1 minus 10, which is less than 0.1. Well, let's go ahead and get this 10 out of the way just to clean it up a little bit more. So we can go ahead and say that we have 9.9 is less than x squared plus 1, which is less than 10.1. All right, so this gives us something we can work with. So now, in order to figure out what our delta is, we have to figure out what our x. We can go ahead and work backwards and find our x in order to find our delta. So what we can do is we can set up two equations. We can go ahead and set up x squared plus 1 is equal to 9.9 on one side. And then we can go ahead and just take out that 1 and give us x squared is equal to 8.9. If we work from the other side, we can go ahead and get, from the other side we can get x squared plus 1 equals 10.1, and then which gives us x squared equals 9.1. Well, we can now go ahead and just solve for our plane x. So x is going to approximately be, for 10.1, is going to approximately be 3.02. For our lower x, we can go ahead and approximate x to be 2.98. Well, we can go ahead, since we know that that's how far away we're going from x, we can go ahead and use that to guess our epsilon. So let's go ahead and do our absolute value of 2.98 minus 3 equals, and that's going to come out to 0.02. Now let's go ahead and check the other side. So now we can go ahead and we have 3.02 minus 3 equals 0.02. So therefore, our delta has to equal 0.02. So we know that for y to be within 0.1 of 10, then x has to be within 0.02 of 3. And if you ever do this and our values, so if our lower and higher estimates don't match, you're going to use whichever one of these values you solve for delta. The smaller one is what you're going to use because you want to make sure that value is true no matter what. So then I'm going to go ahead and so then now that we have that out of the way, let's go ahead and just define one more quick thing and we'll move on to another example. It's also important to note that we can also let this apply to left and right hand limits. So if we have our left hand, so we're taking our left-handed limit, and we know that's going to equal some value. Well, we know that was going to work if for every number of epsilon that's greater than 0, there is a delta that is greater than 0 such that a minus delta is less than x, which is less than a. And that also takes us to knowing that there is some f of x minus L that is less than our epsilon. Our right-handed limit is almost the same thing. The only difference is just what side we're actually looking at. So we're taking our limit from the right side, and then let's just go ahead, abbreviate this, and it's essentially saying the same thing. So we're taking it up, and it starts changing. So we know that we have, when we take our right-handed limit, we know that that's true if for every number of epsilon greater than 0, there is also a delta that's greater than 0 such that we have a is greater than x, which is greater than a plus delta. And then essentially, once again, because that exists, there also exists an epsilon greater than the difference between our f of x and our limit. So let's go ahead and just show how we can go ahead and apply this to just one-handed limits. So let's say we have a piecewise function. Let's go ahead and define this as f of x equals x plus 1 for x is greater than 0 and negative x minus 1 for x is less than or equal to 0. Well, we want to find the right-handed limit as x approaches 0 from the positive of our f of x. So if we're going from the positive, we know it's going to be the top one, so x plus 1. And we can go ahead and just guess that that is going to equal 1. So just to go ahead and plug this in real quick, we go ahead and we can say, since we're using our right limit, that we know our a is going to be 0, which is going to be less than some x, which is going to be less than some delta, because once again, our a is 0. Because we know that, we can also go and infer that we have some absolute value of our function, x plus 1, minus our estimated limit of 1, which is less than our epsilon. All right, so well, we can go ahead and take this down to be x is less than epsilon. Or well, right now we have the absolute value of x, but what we can do, since we know that this has, since we're taking this from the positive side and we know this function is always positive, we can just say x is greater than epsilon at this point, or x is less than epsilon. So now that we have this, we can go ahead and see that we have our x is less than our delta and our x is also less than our epsilon. So we can go ahead and guess that our delta equals our epsilon. So essentially what we do is we go ahead and go back what we did earlier, and we plug in, and we have our x plus 1 minus 1, so our f of x minus L, Well, we know that is equal to absolute value of x, which we know is going to be, since we're already defining it as being positive, we know is x, which is less than our delta, which we know is equal to our epsilon. Therefore, we get epsilon back out, and this, once again, this shows that this works when we're using just one-sided limits. So if we have time at the end, I'll go over a much more challenging example to see what happens whenever some of these don't always work out quite as easily. But for now, let's go ahead and move on to continuity. All right. So let's go ahead. All right, one more thing before we move on to continuity is infinite limits. Let's just go ahead and do our quick definition of infinite limits. So our precise definition of infinite limits is saying, let some function f be a function defined on some open interval that contains the number a. I'm going to type this out because that is going to be faster. Except for possibly a itself. In our limit, I'm going to leave some space to draw that out right there. Then the limit, as x approaches a of f of x equals infinity, that applies if for every positive number m, there is a positive delta such that if we have, so that we have some delta that is a distance from x, then our f of x is always going to be greater than m. So let me go ahead and draw this back in. That way you can see exactly what we're talking about. So we have such that if 0 is in between, so if we have our distance, x minus a, is in between 0 and delta, then our function is going to be greater than that m. So essentially what they're saying is that if we have some graph where the function approaches infinity at some point a, and we define some value m is going to help us to define what our delta is. And essentially it's showing that there's always going to be, if we have our limit going to infinity, there is always going to be more function there's always going to be some more function above whatever we decide m to be. We could say m is a billion, a trillion, bigger than that. That is still going to keep getting, that f of x is going to keep getting bigger and bigger and bigger. That's what it's saying. And essentially, we can go ahead and do the same thing whenever we're looking at, whenever our limit is negative infinity, but the difference is that there's always going to be more and more function below our y equals, in this case, would be n. So if we have more time after continuity, I will also come back. I will also try to come back to this as well, but I want to make sure we do have time to cover continuity before we move on. So let's go ahead and think about what continuity is. So a function, by definition, a function is continuous at some number a if are the limit as x approaches a of our f of x is in fact f of a. So now, if the limit does not exist, and if f of a is not defined, if one of those is true, then our function can't be continuous. So a function can be considered discontinuous if it's not continuous. So let's go ahead and just look and see real quick, take a look and see if we can figure out what happens if we have a discontinuity, or if we can be able to spot discontinuities. So let's say we have the function x squared minus 9 over x plus 3. Well, our graph would look something like this. It's where we have a hole right there at x equals 3. Well, we can say that our function is continuous when x does not equal 3, because we have that little hole right there, but otherwise it's fine. So now let's go ahead and look at the function. Two plus 3 over x squared. So let's go ahead and take a look at our graph. That is going to look something like this. Well, this function cannot exist when x equals 0. So we know that it's continuous when x does not equal 0. And now lastly, we have a piecewise function. It's where we have x squared when x is greater than or equal to 1, and x minus 2 when x is less than 1. So our graph right here will look something like this. So we have our 1, and then we go up like in the square function. And if we are approximating at 1, we're at -1, and we're going down like this. So we know, this one's weird. So we know for a fact that there's a so we know that this function is continuous, since otherwise it's fully continuous. When x does not equal 1. So let's go ahead and look into why the discontinuities work the way they do. So let's go ahead and go back to that first one. So if we have a function, so that first one, this doesn't work because f of a was not defined. It just doesn't exist. That second one we had, this one has an issue because it goes to infinity. Once again, f of a doesn't really exist. We can tell where f of a is going, but that limit technically does not exist. And this other one, it didn't work because essentially our limit, that limit does not exist. We can be able to describe each right-handed limit, but because we can describe our left-handed limit and our right-handed limit. But because those aren't the same, this can't exist. Our limit does not exist. This brings us to our 3 different types of discontinuities. So this right here is our removable discontinuity. Removable discontinuities are easy to spot if you have a graph because essentially they're going to be completely continuous. They're going to look like one complete graph, but maybe with the hole somewhere in there. And they're called removable because essentially you could turn this into a piecewise function and just say, oh, this function exists where that limit exists. So you could just go ahead and just essentially fill in the hole. Now we have our next type is going to be our infinite discontinuities. This is pretty self-explanatory, but an infinite discontinuity is because your limit at that point goes to plus or minus infinity. Lastly, we have our jump discontinuity. Our jump discontinuity is named because it essentially jumps from one point to another at that point. So, and usually you can go ahead and, like we said, we have our stipulations for what being continuous means, and therefore what it means to not be continuous, and you can go ahead and use that to kind of determine what kind of discontinuity it is. So now that we have that, we have a couple of things that I need to go ahead and define real quick. All right, one last thing I need to go ahead and go over before we start messing into all the theorems and such. You can have one-sided continuities. So essentially, that means like if you can only take the limit from one side, then that can count. So for example, on that jump discontinuity, we could essentially say that it was continuous from each certain side, but we can't say the whole function was continuous. And let's see why we can say one-side continuities are okay. So let's go ahead and think about, and let's find what continuity on an interval is. So continuity on an interval is essentially sort of what we've been doing. We're just, instead of looking at a full function, we're looking at part of a function. So essentially we're looking for a function to be continuous on an interval. So we're looking at the continuity. At every value on some interval and essentially if we can see discontinuity on that interval, it's discontinuous. If everything is, it's fine. And if only one side of the endpoint is defined, you can just use the one-side limit. All right, because some functions, their domains are limited, so you may only be able to use one side. So, like for example, if we had the graph, so for example, if we had the function square root of x, we know that the domain is going to be when x is greater than or equal to 0. So we can go ahead and we can still take, and let's go ahead and let's say we want our interval to be from 0 to 2. We can still tell if that's continuous. And it is continuous, but we're allowed to say that because we can essentially just go ahead and just take that positive point. We can just go ahead and approach just from that right side. That's okay. So now there's a couple things that we need to go ahead and look at. So let's say we have multiple functions. Let's say that we have a function f and that's continuous. And let's say we also have some other function g of x, and that one is also continuous. Then essentially we can say that f of x plus g of x is continuous. So yeah, all of these are continuous. F of x plus g of x is fine. F of x minus g of x is also fine. We can also say that if we have some constant c and multiply it times either one, that's also fine. we can multiply them together. Once again, it's continuous. Five, we can divide them, but there's a caveat to that one. It's because g of x cannot equal 0. Otherwise, we're going to have issues. And also, one other thing can apply. We can also say that any composite functions are fine. Because essentially what we're saying with all of these in a way is saying that if you have a continuous function and another continuous function, no matter how you combine them, they're always going to be continuous. So now let's think about, just to make life a little bit easier, let's think about what kind of functions are always going to be continuous. Or to put it, or let's go ahead and narrow it down. What functions are continuous on their domains? Well, the good news is it's almost every function. So the ones that are going to be continuous on all their domains are going to be polynomials. And polynomials, remember that their domain is going to be for pretty much any polynomial where your exponent is 0 or greater, then that's going to exist everywhere. That essentially for them, for polynomials, if their integer is greater than 1, they can go ahead and their domain is going to be from -infinity to infinity. Other ones that can also be continuous are going to include rational functions. But remember our caveat to rational functions, as we saw earlier in our last example, is that you cannot have 0 in the denominator. If you get 0 in the denominator, once again, you are in trouble, and you're just either going to have a discontinuity there. So if you want to look on an interval, that's fine. Or you just say it's just discontinuous at that point. Let's see, we can have root functions. Now, root functions typically have limited domains, especially if they're even numbered roots. So square roots, fourth roots, all of that, those are going to have limited domains. We also have our trig. And some of these will have restrictions as well. So for example, the tangent function, that one does not exist. That one does have discontinuities. Our inverse trig. Once again, you have to watch the domains on those because those definitely have a lot of discontinuities if you look at full intervals, but on their domains, they are continuous. Our exponentials, and lastly, our logarithmic. All of the, like I said, all of these will be continuous on their domains. Now, their domains, they may have gaps in them, but they will be continuous whenever their domains exist. So now let's go over, now that we have all of that out of the way, let's go over the intermediate value theorem. Before we can go ahead and simplify this to IVT. So if we have our intermediate value theorem states that if we have some function f, or f of x, is continuous on a closed interval from a to b, and our capital N is any number between our f of a and f of b, where our f of a does not equal our f of b, then there exists a number called c in the interval from a to b, and we cannot count a and b since those are already defined, and that's going to be such that we have some f of c equals n. So this is derived from like the idea of interpolation. So essentially, let's say if we know we have a lower value and we know we have an upper value and we know everything is continuous between there, we can essentially think of any median value between there. Anything that could fall between that lower and upper value, something exists there. It's just how do we find it? So let's go ahead and do a quick example of intermediate value theorem. So let's go ahead and do the example. So let's think, is there a root on the interval 1 to 4 of the function x squared minus 3x minus 2? Well, hypothetically, you could graph this, but let's pretend that this is a test. You don't have a graphing calculator. So first thing we can try to do is see if we can factor it, but yeah, there's nothing we could really do. This doesn't factor. So let's go ahead and try to use our intermediate value theorem. So let's go ahead and look at each of our endpoints. So let's go ahead and see what happens at f of 1. Since this is a polynomial, we know it's going to exist in every value. So let's go ahead and look and see what happens. So our f of 1, we get 1 minus 3 minus 2, which is going to be equal to negative 4. All right, now let's see what happens at f of 4. F of 4, we get 16 minus 12 minus 2, which equals 2. All right, so we can see that our y range is going to be from negative 4 to 2. So we can go ahead and say because that's true, and we also know that 0 falls somewhere in between negative 4 and 2, then there must exist some x value that will give us a y value of 0. So we know f of c equals 0 exists. So let's go ahead and just try to see, and we could stop there and say that the root exists, but let's go a little further and just try to solve it just for our amusement, because usually they will try to ask you to find c. So we know that our y value is going to be 0 equals x squared minus 3x minus 2. Well, this is nice since we already have 0 on one side of the equation, so we can just go ahead and use our quadratic formula, which gives us 3 plus or minus the square root of b squared, which is 9, minus 4ac all over our 2a, which is going to give us 3 plus or minus the square root of 17 over 2. Well, we can go ahead and just use some basic estimation. The square root of 17 is going to be close to 4. So we have 3 plus or minus 4 over 2. So therefore, the positive one's going to be the one we're going to use because that's going to give us something around 3.5. All right, so now that is the last main topic that I want to cover, but I'm going to go ahead and do a little bit more examples from our epsilon delta limits because those are usually pretty challenging for people to do, especially when they start getting to be polynomials. So I'm going to do an example of that. So let's go ahead. Where are my notes at? Here they are. So let's say they want us to prove that the limit as x approaches 4 of x squared plus x minus 11 equals 9. All right, so let's go ahead and just get started with our basic setup. So we have our x minus a, so x minus 4, which is going to be less than our delta. We also are going to have our f of x minus o, so we're going to have x squared plus x minus 11 all minus 9, which is less than our epsilon. So let's go ahead and let's see if we can go ahead and do anything more with this. So we now have, let's go ahead and combine, so we get x squared plus x minus 20, which is all less than epsilon. Well, we can actually go ahead and factor this out to where we get x plus 5 and x minus 4, which is less than our epsilon. Well, good news is that we have x minus 4's in both equations. The problem is we have this x plus 5 right here, and we can't, and that one's a little harder to mess with than if that was just, say, a constant like we had in other ones. But we can still actually do something with that. So what we can do is let's go ahead and say that x plus 5 is going to be less than some arbitrary constant c. So that can just go ahead and get things out of the way for us. So we can go ahead and plug this back in to where we can say, to where we have c times x minus 4 is less than epsilon, which gives us x minus 4 is less than epsilon over c. So that's something we can actually work with now, since now we have e over some constant. But now we need to think about what we're going to do next. So what we can do, if we're looking at this, so ultimately what we're doing is we're looking at the limit as x approaches 4. So what we can go ahead and do is essentially play around with RC and just say the RC has to be kind of small because we're wanting to ultimately look and see what's going on near x plus 4. So let's just go ahead and we can go ahead and let c equal 1. And we could plug in any value we want for c, but 1's easy to work with, and that's going to let us be close to x equals 4. All right, so now what we're going to do is play around with some stuff. So, wait, actually, wait, I misspoke. So, e over c is going to be 1. So let's go ahead and plug that back in. So we have e over c equals 1, to where we get x minus 4 is less than 1. Well, what we can do is we can go ahead and get rid of this absolute value and say that we have negative 1 is less than x minus 4, which is less than 1. Well, from here, we can go ahead and isolate x on its own, to where we have 3 is less than x, which is less than 5. Now, since we have x isolated, we can actually find and relate this back to that x plus 5. So what we can do is we can add 5 on both sides, add 5 on each side, to where we get 8, which is less than x plus 5, which is less than 10. Now we're moving somewhere, because knowing that that 10 is greater than x plus 5, and we know that c is greater than x plus 5, we can go ahead and say that c equals, we can go ahead and say that c equals 10. So this brings us, so we can plug that back in up here and say that x minus 4 is less than e over 10. So there is one little more thing I have to think about, though. We said earlier that the epsilon over c is going to be 1. But we also have this epsilon over 10 that we also can use. Well, we always want to use the smaller value of whatever, we want to use the smallest value for delta we can get, so we make sure that everything falls into the proper range. So what we're going to do is we're going to write this and say our delta is going to be equal to the minima, to the minimal value of our set, which in this case is going to be 1 or epsilon over 10. So for example, if after we have our relationship between epsilon and delta established, whenever we want to establish what delta and epsilon are, like, so let's say if we get epsilon equals 11, we'd want to use that 1 for our delta. If we get 9 for epsilon, we'd want to use that epsilon over 10. So now let's just go ahead and prove that our values are right. So once again, earlier we said that we have our absolute value of x minus 4, which is greater than 0, but less than delta. Well, we know our delta is going to be equal to that minimal value, or we're trying to prove that's that minimal value of 1 in e over 10. So let's just go ahead, since really epsilon is what we're concerned about with right now. So we're going to go ahead and look and see what happens when we have our x minus 4, which is less than our epsilon over 10. So now what we're going to do is we're going to go ahead and start plugging back in like we normally do and just kind of work our way backwards. So we know that what we ultimately want to get to is to where we once again end up with x squared plus x minus 11 minus 9. So our f of x minus L is going to be less than our epsilon. And we also started off with our x minus 4, which is less than our delta. Well, let's go ahead and look right here. So once again, we can go back and say that we have x squared plus x minus 20. And once again, this gets us back to x plus 5, x minus 4. So from here, we can actually say, since we established earlier that x minus 5, which is less than c, and that c is equal to 10, we can say that we have 10 times x minus 4. Well, we can also say that 10 times x minus 4 can also end up coming out to being 10 times whatever. Since we have the x minus 4, we can relate that to our delta. And since we related delta to saying is epsilon over 10, you can go ahead and cancel out these 10s, which is going to get us our epsilon, which brings us right back to where we started. So therefore, we have proved that that epsilon over 10 is going to work. And that's going to be a valid relationship between delta and epsilon. So let me see if I have any other examples between either two that we could work on. Let's go ahead and do an infinite limit problem. Because continuity in general is a little bit easier to work with, whereas I know a lot of students historically struggle with epsilon delta limits. So let's go ahead and think about our infinite limits. So let's say we're wanting to prove that the limit as x approaches 0 of 1 over x to the 4th equals infinity. So let's go ahead and think about what we said earlier. We have our graph. It's going to look something like this. We can obviously see that that limit, just looking at the graph, is going to infinity, but we need to be able to actually prove that. So we know from earlier, if we go ahead and plug stuff back into our theorem, that we get 0, which is less than, we can go ahead and just say absolute value of x because our a is 0, which is less than our delta. We also know that our function 1 over x to the 4th has to be greater than some number m. So we can play around with this and say, let's move things to the other side to where we get 1 over m is greater than x to the 4th. Well, we can go ahead and move that further and say that we get the 4th root of 1 over m is greater than x. All right, so now that we're here, let's go ahead and rewrite this a little bit cleaner. I'm going to write this the other way just because I also like having it the other way. So we get the 4th root of 1 over m. And actually that 4th root of 1 over m, we can rewrite that as 1 over the 4th root of m. So now that we're here, and we actually are back to having this x right here, since we know that x has to be positive, we can kind of ignore the absolute value sign. We can actually go ahead and say that our delta is equal to 1 over the 4th root of m, but we have to go ahead and check that real quick. So let's go ahead and plug everything back in to where now we have 0, which is less than absolute value of x, which is less than our delta, which we have said is 1 over the 4th root of m. Well, now from here, we can go ahead and let's think back to what we had earlier. So we know that x is going to be less than 1 over the 4th root of m. So now let's go ahead and take the 4th and take everything up to the 4th. We now get x to the 4th is less than 1 over m. Well, we can move stuff back across, and so we are left with m is less than 1 over x to the 4th, which is what we just wanted to make sure improve. So that should be everything for epsilon delta. Let me see if I have anything else I want to just jump on real quick for continuity. I believe that should be all of my examples for today, unless anyone wants me to cover anything else real quick or do a quick example over anything. All right, so that will go ahead and conclude our session today. Once again, everything will upload to the Peer Tutoring YouTube channel within a couple days. All right, have a great day, everyone.